Okay, welcome back. We're beginning chapter 18 today, but before we do, I just wanted to finish up our conversation on biological decarboxylation. Uh, and just to put this in context, we've seen that decarboxylation can happen when you have a beta keto acid. And the reason it can happen is because what's left behind after decarboxylation is resonance stabilized. So you can look at a beta keto acid and think of this, the alpha and the beta carbons with the ketone on it, as a leaving group, or another way to think of it is an electron sink. It's a place for electrons to go. What we'll do with the carbonyl is very similar to what we've done with tetrahedral intermediates. Lone pair electrons on the oxygen kick down and the leaving group leaves. And the reason it can leave, as I said, is because it's resonance stabilized. So whether or not something can undergo decarboxylation is all about whether the thing that leaves is stable or not with the negative charge that's left behind, right? See, the electrons in this carbon, bond between carbonyl carbon and alpha carbon, end up left behind. And you've spent a whole semester and a half learning about what stabilizes negative charges, what stabilizes electrons. Resonance is one of those things. So you can tell when decarboxylation is a possibility when the thing in green that gets kicked off is resonance stabilized. So you saw some examples of that last time. Just as a preview of some fun biology and biochemistry that we'll get to later on in the class, this is not a beta keto acid. This is an alpha keto acid. You expect beta keto acids to undergo decarboxylation easily. Alpha keto acids shouldn't. The reason is the electrons that would be left behind if a lone pair kicked down and kicked this group off, those wouldn't be resonance stabilized. They'd be localized. There's really no place for them to go. If you're having a hard time envisioning what I'm talking about, we're looking at something like that, which you've basically never seen. That's the conjugate base of an aldehyde, and we never ever make that. It turns out that nature has an elaborate strategy for decarboxylating alpha keto acids. The one I've drawn for you here is called pyruvate, and you better hope nature has a strategy for decarboxylating pyruvate, because otherwise we're all dead. So we'll get to that later. For now, let's look at decarboxylation of histidine to make histamine. And you can, looking by that same analogy, you can tell that this is not going to happen on its own without help, because if we did the decarboxylation, if we made the conjugate base of this acid, and if electrons kicked down and then left, they would just be left on that carbon, not resonance stabilized. So that's just a regular negatively charged sp3 hybridized carbon, not resonance stabilized, highly, highly unstable. There's no place for electrons to go. So the whole point of using PLP is to provide the electrons a place to go. Let's see how that changes things. As I said, we're going to use PLP, which is an aldehyde. I'll highlight the aldehyde in, I guess I chose blue. Oh well. You can live with that. We'll highlight the aldehyde in blue. We're forming an imine between the amino group of the histidine amino acid and the aldehyde group of PLP. That imine functional group is here. And what I intended to show you last time, we'll make this the conjugate base of the acid. What I intended to show you last time is, here's the electrons in the bond between the alpha carbon and the carbonyl carbon. And now that we've made the imine, the electrons have some place to go. Indeed, all of what I'm going to highlight in green now becomes part of a good leaving group. And the reason it's a good leaving group is because the resulting negative charge on what's now the alpha carbon is going to be resonance stabilized. So if we draw the decarboxylation like this, CO2 is here, that's where our carbonyl carbon is. And then let's draw everything that's left behind. There'll be a negative charge on what used to be the alpha carbon. Then here's the nitrogen of the imine. Here's the carbon-carbon pi bond in the imine. And I want you to pay attention to the fact that this leaving group is neutral. Negative formal charge on the alpha carbon, positive formal charge on the nitrogen. And I want you to pay attention to the fact that that negative charge is conjugated to that ring and to the positively charged nitrogen. In other words, I can draw a resonance structure of this leaving group that looks like this. All I'm going to do to get from one resonance structure to the other is to push arrows like this. And then I will draw the new set of bonds in red. So that just shows you PLP acts to stabilize the negative charge on the alpha carbon by resonance, okay? Which makes it a decent leaving group. Now, when CO2 leaves, after the decarboxylation, CO2 is gone. That's not reversible. I'm going to erase these arrows briefly and then just show you what happens when I protonate this molecule on the alpha carbon using some acidic group, probably from the enzyme. At this point, I'm going to abbreviate the whole PLP group because we're almost done. Then we do imine hydrolysis. That's going to break the bond between nitrogen and it's going to break the two bonds, the sigma bond and the pi bond between nitrogen and the carbonyl carbon of PLP. PLP gets released, and then we get histamine, which is involved in allergic responses and other things. So anyway, biology has some creative ways of catalyzing decarboxylation reactions, but they're all involved in stabilizing the negative charge that's left behind when CO2 leaves. All right, there's a section on that in the text. You can look at the arrows if you want, but we've talked through it in pretty much the detail that I want you to be able to know. You clearly don't need to memorize the structure of PLP, but it's highly important for you to be able to know why decarboxylation can happen, and we've explained that the resulting left behind group is resonance stabilized. Okay, anything more you want to ask about that? Okay, chapter 18, yes, please.
So, what takes longer to deprotonate the oxygen on the carboxyl?
Good question. What deprotonates the oxygen on the carboxylate group? The pKa of a carboxylic acid in an amino acid is around 2. That's a little bit lower than a typical carboxylic acid, which has a pKa around 4. That's because of the influence of this nearby electronegative nitrogen. In any case, at physiological pH, pH 7, that proton was gone anyway. So that's, I didn't show it from the beginning. I probably should have. Anyway, I just drew the negative charge because that's how it would be at physiological pH. While we're on the subject, at physiological pH, this nitrogen would probably be protonated as well in its ammonium form. It's got to be deprotonated first before you can form the imine, which is, I'm glossing over a lot of that stuff. But okay, others? All right, well, chapter 18 is now, we've spent a lot of time using enolates as nucleophiles, but so far they've just attacked boring old alkyl halides in sort of SN2 type reactions, or slightly more creatively, they attacked bromine as an electrophile. Now we're going to see in chapter 18, enolates attack other carbonyl compounds. So the enolate is going to be our nucleophile, and then some other carbonyl compound is going to be the electrophile. And we're going to mix and match. The enolate could be from an aldehyde, a ketone, or an ester, and the electrophile could be from an aldehyde, ketone, or an ester. And just as a preview, most of the time in the first part of this chapter, we're going to be attacking at the carbonyl carbon, but later on we're going to see what happens when we introduce an alpha beta unsaturated carbonyl carbon. So the theme of OCHEM is nucleophiles attack electrophiles. We're just going to sort of mix and match what the nucleophiles are and what the electrophiles are. So we'll start with the reaction that's called the aldol reaction, so named because the initial case, as it was discovered, was an aldehyde reacting to form an alcohol. So let's give you an example of an aldol reaction. And to set this up, I want us to think of all of the things that can happen to a carbonyl compound in a basic aqueous solution. Okay? So here is an aldehyde, and we're in basic aqueous solution. So one of the things that can happen is if we've got OH minus present, we can either attack the carbonyl carbon or we can remove the alpha proton. If we attack at the carbonyl carbon, we end up, and I'm not intending to show a mechanism here, you could draw the mechanism if I ask you to, but of course in aqueous solution, slightly basic, you're going to form some of the hydrate. That's the product that happens if hydroxide attacks the carbonyl carbon, you get a tetrahedral intermediate, you protonate on the oxygen. And there's some equilibrium constant here, and it's basically a function for how electron poor the carbonyl carbon is. Then we discussed how there's some equilibrium between this aldehyde and its enolate. The pKa of the aldehyde proton is 17, 18, 19 or something like that. So we expect to form a very small amount of enolate. which we could draw like this. Probably, you know, greater than 99% in our keto or aldehyde form, and maybe less than 1% in our enolate form. And of course, that enolate is resonance stabilized. And we've shown that you can protonate on the enolate oxygen to get the enol tautomer of the original aldehyde. And the enol tautomer is, as we've said, less stable than the keto form. Now, all of that's review. But in all of that, we were ignoring something. And that is that enolates are, well, we weren't totally ignoring that enolates were nucleophiles. But we were ignoring that aldehydes are electrophiles. And we were not dealing with the fact or the idea that what if our enolate nucleophile, which we're only forming in like less than 1%. So that enolate nucleophile is going to be in the presence of a lot of aldehyde starting material. What if the enolate alpha carbon attacks as a nucleophile the aldehyde? Now, if the enolate attacked the aldehyde by simply removing the alpha proton, that's a boring reaction. It just trades one enolate for another. That's probably going on. It's not important because it doesn't change anything. But what if the enolate attacks the alpha carbon? So let's show you what would happen there. And this is this kind of thing of an enolate attacking the carbonyl carbon of another carbonyl compound is going to be the major theme in chapter 18. So we'll use orange for electrophile, we'll use purple for enolate. Push the arrows, oops. Let's have, alpha carbon attack the carbonyl carbon, we get a tetrahedral intermediate. I'm going to use an equilibrium arrow here because what happens, this step is reversible. Here's the negatively charged oxygen. Here's the new bond we just made. Oops, that's. So in purple is the portion of our molecule that used to be the enolate, and in orange is the portion of our molecule that used to be the aldehyde, nucleophile and electrophile, respectively. Now, why did I use a reversible arrow here? I'm communicating that it is totally reasonable for the negatively charged oxygen to kick off the enolate leaving group. Why? Because it's resonance stabilized. Okay. So then what happens? Well, aside from going backwards and kicking off the enolate, there are no other leaving groups attached to our orange, what used to be carbonyl carbon. So the only other thing that can happen, and we're under basic aqueous conditions, is for the negatively charged oxygen to pick up a proton from water. Why don't I have it pick up a proton from hydronium? Because there's not very much hydronium in aqueous basic conditions. That's another way of saying the pH is really high. Whoops. All right. So our product of this aldol reaction, we take a single aldehyde and we use part of it as a we use some aldehyde as nucleophile and some as electrophile. This product is called a beta hydroxy carbonyl compound, or beta hydroxyaldehyde, because we've got a hydroxy group on the beta carbon. Creative, huh? And this is an example of an aldol product. In organic chemistry, hopefully you're learning it's useful to recognize structural patterns as characteristic of certain reactions. The aldol product is a beta hydroxycarbonyl compound. And so if you see a beta hydroxycarbonyl compound, you need to be thinking, I could have made that via an aldol reaction. I used reversible arrows here because it is totally reasonable and a possibility for a negatively charged hydroxide group to deprotonate, the beta hydroxy group, taking us backwards here. When a reaction is an equilibrium reaction, like the aldol reaction, the outcome is determined purely by the stability of the products relative to the starting materials. And in general, what we're doing here, if you look, is we're replacing a carbon pi bond and a carbon hydrogen sigma bond with a new carbon sigma bond and a new carbon oxygen hydrogen sigma bond. So thermodynamically this is downhill and it's reasonable, but we will see examples where you can go backwards. In fact, metabolism involves backwards or retro aldol reactions, and that's very important for the conversion of glucose into pyruvate. We'll learn about that when we learn about glycolysis. Okay, questions so far about this mechanism? Go ahead.
Is the E1CV reaction to like dehydrated, is that also reversible, or is that?
Yeah, we haven't talked about that yet, but we will, and it is reversible, yeah. Other questions before we go there? Okay, so experimentally it's observed that sometimes instead of the beta hydroxy aldehyde product, you get a dehydrated version. Here's the, I don't like how I drew that. Here's the carbonyl carbon, the alpha carbon, and the beta carbon. And comparing those two, look at what's missing. We're missing a proton on the alpha carbon, and we're missing an OH group on the beta carbon. And so this looks like this process is called dehydration. It's essentially an elimination reaction. If you think about OH minus as the leaving group and this proton is adjacent to the leaving group, you can start to propose some possible mechanisms from 351 for how this dehydration reaction might happen. Let's consider the possibilities. If it were an E1 reaction like you learned in 351, the leaving group would need to leave first to give a carbocation, and then the adjacent proton would be removed. It's a problem here. We're under basic conditions, and OH minus is a pretty bad leaving group. Okay, so probably not E1. Let's think about E2. For E2, the nucleophile removes the proton as the pi bond's forming, as the leaving group's leaving. But in all the E2 reactions we did in 351, you needed a good leaving group. And again, OH minus is not the best leaving group. So it's probably not E2. There's another possibility that you didn't learn about in 351. It's called E1CB. This stands for the conjugate base version of E1. E1 versus E2, remember, it's probably in ancient history now. You're going to have to dig it out of your brain. But if you recall, the 1 and the 2 refer to how many molecules of things are involved in the rate determining step. For the E1 reaction, the leaving group leaving was the slow step. There was only one thing involved in the rate determining step, and that was the molecule with the leaving group on it. The second step, which was base removes the proton, was really fast and didn't show up in the rate law. For E2, both the base and the thing with the leaving group were involved in the rate determining step. In E1CB, we're back to only one thing being involved in the rate determining step, and that thing is the conjugate base. So E1CB involves proton removal. I'm sorry, but you're out of the splash zone, those of you in the front row. I'm spitting, sorry about that. Gross. Proton removal is fast. The slow step is leaving group leaving. You actually make the conjugate base first. And the base doesn't show, the base that causes that deprotonation reaction is OH minus. It doesn't show up in the rate law because this step is not the rate determining step. It's fast. So hydroxide is going to remove the alpha proton to make the conjugate base, which actually, I mean, you know you can remove a proton from the alpha carbon. We just made an enolate. This is the conjugate base. This is where the CB comes from in the so-called E1CB mechanism. And then leaving group leaving is the slow step. There's only one molecule involved in leaving group leaving. That is electrons kick down and kick off the OH group. OH group can leave now. It's a decent enough leaving group if the kicker offer is already a negatively charged carbon. And that gets us to the dehydrated aldol product. And we could also call this an alpha beta unsaturated carbonyl compound. And in that alpha beta unsaturated carbonyl compound, I guess I'll draw the hydrogen there. These atoms in orange came from the electrophile originally, our aldehyde, and these atoms in purple came from our enolate. All right, questions about that dehydration mechanism? It's new, you haven't seen one like that before. Go ahead.
Is there a way to do it where you like carbonate the OH first so that it makes a good leaving group, which is part of being water?
Great, yeah. Could you do this under acidic conditions? Yes, you can do the aldol reaction under acidic conditions. Going back, your text doesn't show you that. It may have you do a practice problem on that. It's not that hard. Basically, you would use the enol as a nucleophile, and then every other step would be acid catalyzed instead. So yeah, you would protonate the OH group first, and then it would leave. Yeah. Yes?
Is there something that, like, the dehydrated alpha beta, or the alpha beta unsaturated product at the end there, does that hold the reaction to the right?
Yeah, it's a good question. As I recall from your text, it wants you to recognize both the beta hydroxy carbonyl compound and the alpha beta unsaturated carbonyl compound as potential aldol products. If you are predicting products, which should you predict? I have to accept either of them as answers. In cases where the one thing that the alpha beta unsaturated carbonyl compound has that the beta hydroxy aldehyde doesn't have is conjugation between the pi bond of alpha beta carbons with the carbonyl double bond. And conjugation resonance stabilization is favorable. And so it's possible that that makes this product more favorable in certain cases. In particular, if the group you've got over here happens to have double bonds in it, that can help pull you towards this alpha beta unsaturated product. I will simply want you to anticipate both of them as products. I'll accept either of them as acceptable aldol products. In a mechanism question, you'll know where you need to end up though, right? The mechanism question gives you some starting material and some products, and so you'll know where you need to end up, and that'll help you to know what to do. Yeah?
Under acidic conditions, would it become an E2 reaction because of the protonated alcohol?
That's a great question, and I don't know the answer to that. Somebody's probably studied it.
Would you still have the conjugate base E1 because it's under acidic conditions?
I think you'd be. I'm just thinking off the top of my head now. This is certainly not in your text, but I think the question is if you were under acidic conditions. I think probably you're looking at either E2 or E1 because water's not a very good base. I don't know. Is the short answer to that. Good question. All right, others. So that's the aldol. You need to be good at predicting products for the aldol reaction. You need to be good at drawing the mechanism for the aldol reaction, and you need to be good at thinking backwards in terms of synthesis, which is if I show you the aldol products, can you think backwards to what the starting materials would have been? So let's work on that in stages. Let's use a ketone now. Under basic aqueous conditions, this is what we're going to call the self-aldol reaction. So you're going to make the enolate of that ketone. And again, because the pKa of alpha proton on a ketone is much higher than the pKa of OH minus's conjugate acid, you're going to only form a very, very small amount of enolate. It may help you to draw that enolate as one of the starting materials. Okay. So you got 30 seconds, draw what the product is for that self-aldol reaction. I actually want to see both of them. I want to see the beta hydroxycarbonyl compound and the alpha beta unsaturated carbonyl compound. We need to simulate testing conditions. I'm going to sniffle a lot, and if anybody's got a candy wrapper they can crinkle while you guys are thinking, that would be really helpful. I don't know if anybody's ever done that in a testing center. I wouldn't be surprised, though. All right, your 30 seconds are up. No extra time for distraction. What have you got? Somebody tell me what to draw. Okay, that's great. Good start. There is a carbon. Now what? A couple more carbons. Come on, tell me. How many carbons in a chain? Tell me how many of that. You want 5? Okay, now what? I want a hydroxyl group. No. Why don't you tell me where the carbonyl is? Let's number carbons for you. Tell me where the carbonyl is. 2? Why not 4? Fine, it'd be the same thing. Okay, now what else? Alcohol on which carbon? 4. And am I missing something? Methyl on 4. Okay, there it is. Good. Beta hydroxy carbonyl compound. And you were even distracted while I was doing it. And then this is the alpha beta unsaturated carbonyl compound. Good. I want you to be able to think through both of those. Let's think backwards. And I actually want to do walk through the mechanism of a retroaldol reaction. Yes, let's think backwards. This is going to be fun. All right. Fun. All right, so here we're going to see that what I've drawn here is an alpha beta unsaturated carbonyl compound, and we're going to notice that we could have made that via an aldol reaction. So this is sort of a retrosynthesis question. What was the starting material? Now, I know we just triggered the fires and filing cabinets and SpongeBob's in your brain because we drew a 6-membered ring, and suddenly that makes things worse. So let's notice the aldol mechanism. If the product is an alpha beta unsaturated carbonyl compound, we can think backwards to the beta hydroxy precursor simply by losing the double bond. A hydrogen goes on the alpha carbon and an OH goes on the beta carbon. So before we, what was the starting material? Start with the alpha beta unsaturated carbonyl compound, identify alpha and beta carbons, then draw the beta hydroxy carbonyl precursor to that dehydrated product. So to do that, we will simply put a hydrogen on the alpha carbon and an OH on the beta carbon. See what we did? Then go back to the aldol mechanism. Notice that the precursor to the beta hydroxy carbonyl is the deprotonated alcohol. So we're going to take the proton, we'll draw the precursor in which the proton is removed from the beta hydroxy group. And we'll notice that this is the so-called tetrahedral intermediate that we got after the nucleophile attacked the electrophile. Notice from our previous mechanism that tetrahedral intermediate up here, we made a new sigma bond between the alpha and the beta carbons. And the negatively charged oxygen is on the beta carbon. So go ahead and highlight that sigma bond that was made And this will allow us to think backwards one more step to the stage of enolate and carbonyl compound that it attacks. Notice above in the aldol mechanism, prior to the tetrahedral intermediate, the alpha carbon was negatively charged and the beta carbon was your carbonyl electrophile. So I'm going to highlight in orange the part that was our electrophile, and in purple the part that was our nucleophile. I'm going to redraw the molecule, but the alpha carbon is now negatively charged as an enolate, and the beta carbon is now my ketone electrophile. Whoops. And then thinking backwards one more step, run out of space a little bit. Up above, the precursor to the enolate was simply our ketone starting material. So to get to the starting material, I simply am going to put the proton back on the alpha carbon. Okay. So that's thinking backwards through an aldol reaction. Retrosynthesis to see what the starting material would have been. You can go through it stepwise exactly like that, and you'll get the right answer. Alternatively, if you want to hurry along, you can memorize this structural pattern and understand that in the aldol reaction, we make both the sigma and the pi bonds between the alpha and the beta carbons. That the alpha carbon used to be just an enolate, and the beta carbon used to be a carbonyl. So conceptually, you disconnect here. The alpha carbon, you're going to replace each of these sigma, both the sigma and the pi bond, with a proton. And then the beta carbon, you're going to replace both the sigma and the pi bond with sigma and pi bonds to oxygen. So you may, with practice, you may get good enough to the point that you can just jump directly to that. And frankly, it's probably a good idea if you can get familiar enough with this reaction that this is not such a big conceptual jump. That's going to take some practice, and so I'll encourage you to do that. Okay, questions about that, thinking backwards? Trying to decide whether this would be useful. Sure, why not? Let's actually do a retro-aldol reaction. I'm a little bit wary of doing this because I'm afraid I'm going to confuse you. Because the question in your mind is going to be, how do I know whether an aldol reaction is going to go forwards or backwards? And the answer is you don't. You go in the lab and you try it. different sets of aldol reactions, because they're equilibria, will have different equilibrium constants, meaning products will be favored over starting materials by different amounts. Sometimes those equilibrium constants are going to be large, sometimes they're going to be small. It's not really a good question for me to ask you to predict whether a reaction will go forward or backwards if I don't give you the tools to make that prediction. However, if you already know if it's a mechanism question, you already know what the starting materials are, you already know what the products are, then it's totally a fair question for me to ask you to draw a reasonable mechanism, okay? So we drew a reasonable mechanism for the forward reaction. Let's go ahead and draw a reasonable mechanism for the reverse reaction. And again, remember, I'm not telling you what the equilibrium constant is. Probably in this case, it's greater than 1. Probably the products are favored. But it's still a decent question to ask, draw the retroaldol mechanism, okay? So focus on the mechanism. Don't get distracted by worrying about, hand-wringing about, well, how do I know whether or not that was the product? That's not the question. This is not a predict products question now. This is a can you draw the mechanism question. Okay? Is that clear as mud so far? Yes? Okay. What I'll do is we'll let our retroaldol mechanism be informed by, dang it, I only wanted this, I guess. We'll let our retroaldol mechanism be informed by the forward mechanism. So I'm going to copy that, and we're just sort of going to put it up here in the corner. Okay. So suppose we start with, for the retroaldol reaction, let's start right away with the alpha beta unsaturated carbonyl compound. And one of the things you didn't notice was that in the final step of the forward aldol, OH minus is a leaving group, so we should have written it there. Okay, if the final step of the aldol reaction is lone pair electrons on the alpha carbon kick off OH minus, and OH minus leaves from the beta carbon, then what should the forward step, what should the first step of the retroaldol reaction be? OH has got to attack. Now, where's it going to attack? If you didn't know, you might say, well, let's attack the carbonyl carbon. And you can do that, that's probably happening, but it doesn't lead to the appropriate destination. We want to have an OH on the beta carbon. So you need OH to attack the beta carbon. Is that reasonable? What kind of reaction is that? You've seen that once before. What was it? Chapter 13. Cuprates attacking the beta carbon of an alpha beta unsaturated carbonyl compound. This backward step, loss of the OH group, if we go in this backwards direction, this mechanistic step is called conjugate addition. That is, we're adding OH as a nucleophile to the beta carbon of an alpha beta unsaturated carbonyl compound. Okay, so that's it's interesting how the same step looks different when you look at it backwards versus forwards. In the forwards aldol reaction, this final step was an elimination step. but if we run it backwards, it's conjugate addition. Okay, so then that would get us here. Then what? Looking at the forwards step, the immediate precursor to this negatively charged conjugate base is the beta hydroxycarbonyl compound. So what am I going to do mechanistically? Sometimes if you're stuck, just go ahead and draw the structure of the next step, which you can copy down from the mechanism above. Look at the differences between the two, and those differences will tell you exactly what you need to do. So, what do I need to do? I need to get rid of the negative charge on the alpha carbon. You can tell that's true because in the forward reaction, I used OH minus to deprotonate that alpha carbon. We didn't draw it here, but the product of that would have been water. Now compare what we've done here to what was done here. Notice that the products are, and the intermediates are all identical, right? We had OH minus here, we had alpha beta unsaturated carbonyl compound here, same thing here. Immediate precursor, water and the conjugate base, water and the conjugate base. Immediate precursor to that, beta hydroxycarbonyl compound and OH minus, same thing here. Okay? And so we could continue. Here's the, from the forwards aldol reaction, here's the immediate precursor, the tetrahedral intermediate. How could I push arrows to get there? Deprotonate the OH group, okay. Now, without looking above, how do I break that up into two different pieces? Tell me what to do. Form the pi bond, and then what? Kick off the enolate. This is the step that's most likely to be called a retroaldol step, because it's the step where you're breaking the carbon-carbon sigma bond between the two pieces that you would have made in the forward aldol reaction. Okay, and then we're basically done. The last step would be to protonate the enolate to restore the final aldehyde. Okay, that's how you push arrows through a retroaldol reaction. The intermediates are all the same. Notice the reactions, though they're exactly backwards, look a little bit different. Right? We call this basically an E1CB reaction where we're eliminating OH minus from the conjugate base. That's great, but when you run it in reverse, it looks like conjugate addition. And that's okay. The arrows are going to look different when you run them backwards. The intermediates are all going to be the same. You should be good at pushing arrows through the aldol reaction both forward and in reverse. I want to show you one application of a retroaldol reaction from biochemistry. And this is a reaction that's in glycolysis, which is a metabolic pathway that converts glucose into pyruvate, which you can then send after a couple of steps to the citric acid cycle. It's how we get energy. The reaction that we're going to talk about involves something called fructose 1,6-bisphosphate. That's a mouthful. Don't worry, you will have a chance to memorize this structure later. For right now, don't worry about it, but I want you to recognize the portion of this molecule that is basically an aldol product. So 6-carbon sugar, fructose 1,6-bisphosphate. The enzyme that catalyzes this reaction is actually aptly named aldolase. It's an enzyme that catalyzes the aldol/retroaldol reaction. I will tell you that this reaction is an equilibrium reaction. The equilibrium constant's pretty close to 1. This enzyme doesn't care whether the reaction runs forward or reverse. And it's actually useful for biology to be able to go both ways on this one. Though for glycolysis in the forward direction, the forward direction actually corresponds to the retroaldol. So if I were going to say what's the retroaldol reaction that breaks this molecule apart, you would need to first identify the carbonyl carbon, the alpha carbon, and the beta carbon. To confirm that a retroaldol reaction is even possible, you would need to confirm that this is indeed a beta hydroxycarbonyl compound, and it is. You see the OH on the beta carbon? There's also an OH on the alpha carbon, don't care, it's not involved. Based on what we've talked about above, if you can identify the beta hydroxy group, you know what portion of the molecule was your electrophile, and you know what portion was your enolate. So that means this portion of the molecule was the enolate, and this portion was the electrophile. You know what kind of electrophile it was by looking what's attached to that beta carbon. Notice that the beta carbon has an OH group. It's got this bond between alpha and beta carbons. That's the one we would have made in the aldol reaction. And then it's got a bond to a carbon and a hydrogen. So you can tell that this portion of the molecule used to be an aldehyde, and that this portion of the molecule used to be the enolate. Now, thinking backwards through the retroaldol reaction from the beta hydroxycarbonyl compound, our first mechanistic step should be to remove the proton from the beta hydroxy group. We're going to use some group from the enzyme to do that. I'll erase some of these details. Once you've gotten to the negatively charged oxygen, this is the sort of tetrahedral intermediate. Then the key retroaldol step is electrons kick down here and leaving group leaves with the negative charge on the alpha carbon. And so I'll draw for you that sort of retroaldol step. And there's some things we could draw after that, but I don't think we will. I think we'll have made the point. right? This is the orange portion of our molecule, and then here we should be left with the enolate. Huh, how long has it been that way? Did it just barely go to sleep? That's kind of weird. That's not happened before. I think the computer is telling me something about your mental state. Are you guys asleep too? And we're gone. All right. So, carbonyl carbon, alpha carbon, and then what used to be the beta carbon. This is a key step because it splits up a 6-carbon thing that you got from glucose into 2 smaller 3-carbon pieces. This one happens to be called glyceraldehyde 3-phosphate. This one, once we protonate on the alpha carbon, happens to be called dihydroxyacetone phosphate. You can actually isomerize this one into that one. So this allows you to clip what used to be glucose into 2 identical pieces, which you can then use. That way, in all the downstream reactions, you don't need 2 different sets of enzymes to handle the 2 pieces. They actually become the same piece, and then you move forward from there. All right, that's a good pausing point. So let's take 5, and then we'll get back to it.